Okay. So today we're going to be speaking about acids, alkalis, and indicators. So first I'm going to go through a little bit of history, especially the kind of history that you don't have in your books. So let's just get a color that's going to stand out a bit. Okay, great. So in ancient times, people knew that some things would taste sour and some things would feel slightly slippery. And if you use them for washing clothes or whatever you use them for, your skin could become raw and sort of hurt. Literally, yeah. So they would use these kinds of materials, especially lemon juice and potash, to help them clean clothes, keep the white things as white as they could. They also used them in dyes and things like that to dye clothes. So yeah, potash is literally water poured through the ashes from a fire, and it is an alkali. So some of the substances from the ashes will dissolve into the water, turning it into an alkali. And they also knew that if you mixed potash with fat, normally some kind of animal fat that they rendered, so they would literally put the fat from whatever animal in a pot and melt it down until it's see-through. And then they would mix potash into that until it became hard and lumpy. And that would be soap. And soap essentially is just that, some kind of fat mixed with some kind of alkali. And it essentially makes, it's a molecule that has two parts. The one part of the molecule likes water and will stick to watery things, and the other part likes fat and will stick to fatty things. And so that is essentially how you would get things off of your clothes. One of these two ends would stick to it, and then the whole molecule surrounding this piece of dirt would dissolve, would essentially go into the water surrounding this material. So I'm speaking about this as hard block soap, the sort of non-see-through, hard, round, caked soap that you could get. I'm also not speaking about glycerin soap, which is the see-through kind. So I'm talking about the actual, yeah. So we are talking about acids, alkalis, and universal indicators. So that was essentially a bit of a history of what people knew about acids and alkalis and what they used them for. They did not necessarily know how these worked. They just knew it did and how to do it. So then we get to indicators. So an indicator is a dye or colorant that you can add to specific kinds of things, and it would change color when it comes into contact with acids or bases. So there's a few examples. We've got methyl orange, which would turn pink in acids and yellow in alkalis. We've got phenolphthalein, which is clear in acids but pink in bases. We've got red cabbage juice. This is the easiest one, and you can make this one at home. It turns red in acids. It is purple in neutral solutions and normally. And then it turns green or blue in bases. There was a few others as well that was used. Juice from violets, litmus, which is a juice from a specific kind of lichen. And this forms litmus paper, which is either blue or red paper, and then it would turn the opposite color when it comes into contact with either an acid or a base, if it's the opposite thing. So yeah. Then we get universal indicator. So a universal indicator is a mixture of a few different indicators, each of which will change color at slightly different parts of the pH scale, so that you can essentially try to use it to measure using a color gradient how acidic or how basic something is. Normal indicators tend to not tell you how acidic or how basic. It just tells you this is an acid or this is a base sort of thing. So you get different kinds of universal indicator, and their color scales are shown on the bottle or in the instructions that come with them. Red cabbage can be used sort of as a universal indicator, and I will show you guys a video about that in a bit. And then we get indicator paper. So indicator paper is paper strips that have been soaked in an indicator and then dried. So they either soaked them in a universal indicator or in a litmus solution and then dried it out. And then you can use this paper to dip into acids and bases in order to see what color change takes place, whether it is an acid or a base, how much, by comparing this piece of paper on the color scale. So then we get to reactions between acids and alkalis. So this is the basic reaction that takes place, and you do need to know this and word-based reactions. I'm also going to show you the symbol one. You don't need to know that. I'll get to that. So essentially what it is an acid plus an alkali gives us a salt and water. So here we've got one kind of acid. So we have hydrochloric acid. And if we mix it with sodium hydroxide, it becomes sodium chloride, which is table salt and water. Hydrochloric acid is the acid found in your stomach. So this is stomach acid. Sodium hydroxide is one of the things that we can find in antacid tablets, which is essentially something you drink if you have heartburn. Heartburn means that some of the acid from your stomach, there's either too much acid in your stomach or there's just too much things in your stomach. And then some of the acid from your stomach pushes up into your esophagus, making it literally feel very sore, burning. It gives you heartburn. It's a horrible feeling. So then you would drink some kind of antacid in order to try and neutralize some of the stomach acid so that it doesn't hurt you so much. So sodium hydroxide is one of the kinds that we can use. And then our hydrochloric acid and our sodium hydroxide react, and it forms table salt and water. So I just want to show you guys. Here we've got chloric, and here we've got sodium. So here we get sodium chloride and water. So this is hydro. That means we've got hydrogen molecules, atoms over here, and hydroxide means we've got hydrogen and oxygen. And so hydrogen and oxygen gives us water altogether. So this is what I meant with the symbol notation. You don't need to know the symbol notation. You guys need to know the word notations, not the symbol one. I'm showing you this anyway because it is interesting and it tells you what's going on. So hydrochloric acid, so hydro, H, that's that bit, and chloric means it is bonded with a chlorine atom. So that's our hydrochloric acid. And then we have sodium hydroxide. So we have our sodium, and that bit there is hydroxide. So it's an OH combined together. Yeah. Then over here, I will answer that question that came through at the end, since it doesn't really have anything to do with acids and bases, but I will tell you guys. The symbols you will need to know from IGCE and onwards. So after our reaction, we get this part and this part to stick together. So we get sodium chloride or table salt, and then we get water, which is that H, and these OH. So then we get two H's and one O, so we have H2O, which is water. So you don't need to know these symbol reactions. You guys need to know the word ones. These just make it, to me at least, a lot easier to find the word reactions. Okay, this is a simulation, another simulation from PHET Colorado. So I have decided that I'm going to open up a forum so that I can post all of these links and things that we're using in the live lessons there, so you guys can find them very easily. So I will do that. So here we have acid-base solutions. So here we have our solution, and this shows us the molecules that we're having over here. So here we've just got some normal water, and then we've got various different kinds of acids, bases, and things that we can use. So we can dip this bit in, and it gives us essentially just an indicator of the pH. 7 pH is neutral. So that would mean just plain water or something like that. There are different kinds of indicators we can use. Here we have one that shows that current can flow in between, so the light bulb lights up and how strongly it lights up. Apparently not very strongly with this one. And here we've got some indicator paper. So this I can take and I can go dip it in, and then I can move it along the scale and see where on this scale it fits. In this case, it's easier to dip the whole thing in and then to go show you guys like that. In general, we don't dip the whole paper in. We just dip a little bit and then go compare that bit. So here we can see the color matches at about a 7. But let's move on to other kinds of things. Here, if we check the pH, this is a strong acid. It's about a 2. So if we take our indicator paper and we go dip it in, and then we can go compare it along here, we can see exactly where the colors match. So the colors match round about there-ish. So we know that is how strong our acid is. If we have a weak acid and we go dip it in, you can see the color is different. So if we go move it along here, we can see it comes to about there-ish, a 4 about. So if we change it to this, it says it's about a 4.5. So it'll be slightly about there-ish, in between the 4 and the 5 over there. Okay, so let's move on to bases. This was already sort of dipped. So as we dip it, we can see, we can go around here and we can see this is about a 12. If we change to this kind of indicator, we'll see it's about a 12. And if we go to a weak base, it measures about a 9.5. So let's see what our paper does. We go dip our paper, and then we can see it falls somewhere in between those two colors. So that's how we know essentially how our color is over here, what our pH is. So you can go play around with this and go see what is happening. They've got a graph showing you the different ions and things coming. You don't really need to do anything to do with the ions and the molecules. This is more as an exercise in comparing the pHs. So here we get to the other thing. So that was the introduction. Now we get to a solution that you can make. So we can increase the concentration of our acid, and we can make it a stronger acid or a weaker acid. So if we have a weak acid, we can go measure it. It measures about 5.12. So if we go dip in our paper, we can come along and measure exactly where it sits. We can make it slightly stronger. And then if we go measure it, you'll see it goes to about there. So it's a fun way to learn exactly how to do these, how to measure these things, and to use a color scale. So if we change this to bases, then we can essentially go along this scale and find exactly where it fits in on this side. So I will post the links and then you can use this simulation. There's another simulation that I want to show you guys. So this is to do with acid solutions. So now we're not working with pure acids, we're working with solutions, which is essentially how we use acids every day. Acids and bases we tend to use in solutions. So let's add some drain cleaner. So let's add some, about that much, and then we can add some water. So you can go measure the pH and it tells you what the pH is like. And as we add some more acid, you'll see the pH goes up. Take some of this out and add some more water, and that would make the pH go down towards the 7. So drain cleaner is a base, sorry. Hand soap, blood, all sorts of things. Here we have battery acid. So if we add some battery acid, you'll see it has a pH of 1. It's very acidic. So we can go add some water to reduce the acidity slightly and things like that. So you can go play around with that to see what the solutions and things do. Also, different kinds of acids and bases. There's orange juice. Coffee is slightly acidic. Milk is slightly more acidic than water. Blood is slightly basic. It's about a 7.4. So this video over here is from MIT. So that is the Massachusetts Institute of Technology. And they are essentially going to show us how to make a universal indicator from red cabbage juice. Okay, here we go.
Pink.
So he's trying to do some kind of magic trick by pouring.
Hey, not bad. Okay. How about pretty cool science? My name's Tyler, and I'm a student at MIT. And I'm going to teach you the science behind this magic trick. And then I'm going to show you how you can do it yourself at home. But first,
okay, so here
I have all my chemicals that I use for these science experiments that I do every day. And I also brought a few of these chemicals here from home. I also have a bunch of beakers here, and I filled the beakers with a liquid called indicator. You can see that this indicator I'm using has sort of a blue purplish color, and that's going to be important. Indicator tells us whether a chemical is acid, base, or neutral. Let me show you what I mean. I'm going to take a chemical here and add little drops of it to the indicator. See, these drops make a very light purple, and there's some pink, and some more pink, and it gets pinker and pinker the more I add. And now it gets darker and darker, and I eventually get a really deep, bright red. Isn't that cool? If we can add a chemical to this indicator, and it makes it redder and redder and redder, like starts with purple and then goes to pink and goes to red, we call it an acid. So this chemical here is an acid. Let's take a look at another example. Here's a fresh beaker of indicator, and again you can see that it sort of starts at a blue, very light purple color. Now I'm going to take this other chemical and I'm going to add it to the indicator. Let's see what happens now. You can see little bits of green in the indicator as I start dropping this in. And now we go to a really nice blue color, a very bright blue, and then it becomes sort of aquamarine here. It's greener and greener now, and now it turns the indicator green. And I'll show you what happens if we add even more. This gets more and more yellow until we have a yellow solution. And it's this really bright, cool yellow color. If we can add a chemical to an indicator, and it makes it darker blue, or that brighter blue, that really nice blue, and then greener, and finally yellow. If it can make any of those colors when we add it to the indicator, we call it a base. So, acids make it pink and then red, and bases make it blue, and then green, and then yellow, if we add a whole lot of them. Okay, let's look at another example. I have a third chemical here. I'm going to add some of it. Dropping it in here, lots of drops, and I'm not really seeing any change. The color remains the same. And as you'll see, I can add as much of this as I want, and the color's still going to stay this blue purplish color. That's because this compound, this chemical, we call it neutral. It's not acid and it's not base. so it doesn't change the color of the indicator. We can add as much as we want, and the indicator is just going to stay the same color. So those are our three categories of chemicals: acids, bases, and then those that are neutral. You can tell whether something is acid or base or neutral by the color that it makes an indicator. You may think that this indicator is a fancy chemical that I only have in the lab, but actually I made this indicator in the kitchen, back in my house, and you can do the same thing. We're going to need some indicator for the magic trick that we're figuring out, and I'm going to show you how to make this kind of indicator back using, so you can do these in water and use a stove. So make sure you have an adult around to help you with that step. Here's the stuff you're going to need. First of all, you're going to need a red cabbage. You should be able to find something like this at any supermarket. And then you're going to need a pot to boil some water in, and then you're going to need a strainer. And that's it. And it's pretty simple. So what you want to do is you want to take the pot and you want to fill it about halfway up with water. And then you want to take the cabbage and start pulling off parts of its leaves and putting those in the pan. And you want to fill it up until pretty much all the cabbage is covered with water. So this is a pretty good amount right about here. And then what you want to do is turn up the heat and boil the water, let it boil for 4 or 5 minutes, and then turn the heat off and let it sit for 15 minutes, 10 to 15 minutes. And after you do that, what you're going to see is the cabbage is going to lose its color. All that purple dye that was in the cabbage leaves is going to come out into the water. And you're going to end up with purple cabbage juice. And then the final thing that you need to do is you need to take this and, using a strainer, pour the juice off the top of it. And now you have your cabbage juice indicator all ready to go. Let's go and see what we can do with this indicator and then find out how we can do this.
Okay, so that is essentially how you make a universal indicator using cabbage juice. So purple cabbage juice. I see there is a comment that you did do this in the Q&A. That is fine. I just think that this is quite cool, and this is for our standard students as well as our premiums. So here we go. I want to show you guys this video very briefly. I'm only going to show you a little bit of it. He is busy teaching teachers how to do this experiment. So pretty much half of the things he said is not really aimed at you guys. But here we go. So he is
inexpensive, and it can teach a variety of concepts. What I have is and we're going to,
let's just go to, okay, over here. So he's got a beaker of ice water, and he's adding milk of magnesia to it. Milk of magnesia you can probably find at your local pharmacy. It is an antacid that you can buy, and it's this sort of whitish color.
measure that very accurately. Yes, that was 23.95 milliliters, but that'll be very nice. And then what we're going to do at this point is we ask the students to make some observations.
So he added it into the beaker, and now you can see it's a milky white color. So now he's going to add a universal indicator. So he's got his universal indicator over there telling you exactly what the pH scale says. And
observation that milk of magnesia must be a base. And you could talk a little bit about, of course, the antacid properties of milk of magnesia and why they would be taking that when they have an upset tummy.
So now, I want to get to over here. Now he's going to...
It also allows the reaction to go faster, and it allows the volume not to become so diluted as we work with this. So we've got a purple, cloudy mixture that's swirling around with some ice in it. So we add a pipette full of hydrochloric acid, and of course what we see is that we go to the pink side of the process. The students immediately note that we've gone into the acid range of this process. And as we look at it for a moment, The students would become a little impatient. They're going to say, is there anything happening? And all of a sudden, magic takes place. And the solution begins to turn colors again. That's quite captivating because they didn't expect that to happen. So now we come back to the process and we see that we've come into kind of a bluish teal kind of color. Guys have only 8 basic colors, girls of course.
Okay, so he added an acid to the base, which immediately turned the solution slightly more acidic. And as it reacted with the milk of magnesia inside the beaker, it changed colors again. He added the ice to it specifically to slow the reaction down, so you can see the change going through the colors. So before he added the acid, it was this purplish color, and then afterwards some of it reacted and you could see it is now this teal color, so it's less basic than it was. And he continues doing this a few times, and each time you would get a slightly different color blue afterwards. And as you continue, you would eventually see that the milk of magnesia gets used up and you can start seeing through the solution again.